Hello friends, welcome back to our YouTube channel. If you like this video, please like, share and subscribe. I'll share our videos commanded by our experts, so let's begin.
If you like, please like, share and subscribe. So let's begin our today's topic. Let's begin.
We are watching a surge of autonomous machines deploying into the physical world, promising a near future of highly capable humanoid robots and automated fleets. But the immediate reality of these deployments relies entirely on human operators, remotely stepping in to control them and guide them through complex edge cases. This network map shows the hidden bottleneck in the industry. Current fleet management architectures hit a hard, invisible ceiling when scaling, failing to remain stable past a few thousand units. When an operator takes manual control, any slight delay in perfectly synchronizing the high-definition video feed, the audio, and the raw sensor data makes precise physical movement impossible. Even with the most advanced robotics hardware, unlocking physical AI at scale remains a heavy data transmission problem. To solve a cutting-edge robotics problem, the solution is coming from an entirely different era of technology, early 2000s desktop media software. Specifically from Jean-Baptiste Kempf, the lead developer behind the universally recognized VLC Media Player. For decades, VLC maintained a legendary reputation in the software industry for extreme operational efficiency. It was the lightweight application that could flawlessly decode and play absolutely any media format you threw at it. Why has the pioneer of local video playback just emerged from stealth to build the connectivity layer for AI robots? Kempf recognized a crucial mathematical overlap. Decoding and streaming high-density video over unstable networks requires the exact same data mechanics as remote robot teleoperation. He leveraged that insight to found Kyber. The startup is building a real-time control infrastructure layer that functions as a single toolkit for managing remote devices on a massive scale. The market clearly sees the value of the approach. Kyber recently secured $5 million in seed funding, led by Lightspeed Venture Partners, with participation from Ovni Capital and Kima Ventures. The company is moving fast, already deploying a team of 25 specialized engineers stationed across Paris, San Francisco, and Singapore. Kyber provides a foundational software development kit, the essential underlying plumbing required to make massive physical AI operations actually work. In remote robotics, the strictest metric of success is glass-to-glass latency. That is the exact time delay from a photon of light hitting the robot's camera lens to the image arriving at a remote human operator's eye. This side-by-side chart compares standard teleoperation lag against Kyber's engineering benchmark. They have managed to compress that entire complex data journey down to just 8 milliseconds. To see how they achieve this speed, we can look inside the pipeline. Instead of processing sequentially, Kyber tightly synchronizes the heavy video feeds, spatial audio, and raw sensor inputs so they are flowing in parallel at all times. And underneath those flowing data streams, the entire architecture is built on an open-source core, leveraging heavily modified versions of the VLC and FFmpeg processing frameworks. An 8-millisecond delay is entirely imperceptible to human biology. By operating faster than the brain processes visual information, Kyber effectively eliminates the teleoperation lag barrier. With the micro-latency problem solved, Kempf's ultimate vision scales up to macro networking, establishing what he calls planetary-scale device management. While legacy command systems buckle under the weight of a few thousand nodes, Kyber's architecture is built to reliably route data and command millions of machines simultaneously. This diagram illustrates Kyber's commercial strategy, mapping out the massive data flow into 3 specific legacy industries they intend to target. The first vertical is robotics and humanoids, where absolute zero-lag connectivity is required to ensure safe, complex physical operations by remote workers. The second is drone fleets. Here, immaculate real-time data synchronization allows operators to coordinate highly precise movements across vast distances at scale. The third is remote IT access. By leveraging this ultra-low latency technology, Kyber offers a significantly faster alternative to legacy enterprise environments like Citrix. By solving the core transmission problem, Kyber is positioning itself as the critical invisible connectivity layer for billions of dollars of hardware. This infrastructure is already in motion. Kyber has secured initial commercial deployments across the defense, telecommunications, and AI sectors. The practical result is a physical world where massive, highly coordinated swarms of autonomous machines can operate together flawlessly. True to his roots, Kempf maintains a free, open-source core SDK for developers, while supporting the business by monetizing productized versions for enterprise clients. The architecture coordinating tomorrow's autonomous hardware relies on the battle-tested video streaming philosophies of the early internet.
Humans are relatively slow creatures. A fast reaction to a visual stimulus takes us about 250 milliseconds. But for a machine remotely operating at highway speeds or performing delicate surgery, the communication gap must close to exactly 8 milliseconds. In engineering, we measure this gap using a metric called glass-to-glass latency. It is the baseline for determining whether a physical AI system can safely operate in the real world. The clock starts the millisecond a photon hits the glass lens of a remote machine's camera. That visual data must be captured, encoded, routed through a global cloud network, decoded, and rendered onto the glass of a human operator's monitor. We often assume that scaling up robotics requires better motors or more powerful batteries. However, the primary bottleneck is moving and synchronizing that data over the network fast enough to make the hardware useful. Autonomous transit time fluctuates by even a few milliseconds. The video feed falls out of sync with the machine's actual position. This results in telemetry drift, mechanical jitter, and unpredictable operations. Autonomous machines process reality in strict, instantaneous intervals. To maintain control, incoming command streams and outgoing sensor feeds must interlock perfectly. Today, most corporations rely on legacy enterprise tools like Citrix for remote access. Those platforms were architected decades ago to refresh static spreadsheets and text documents. They were never intended to handle the continuous, synchronized, multi-stream data required to pilot a drone. Right now, the largest active device fleets top out around a few thousand units. The next stage of physical AI requires operators to reliably manage fleets of millions of machines simultaneously across the globe. Coordinating millions of machines requires a departure from legacy protocols toward a purpose-built, unified infrastructure. That specific challenge is what a new startup called Kyber aims to solve. Led by Jean-Baptiste Kempf, the company recently emerged from stealth. They've secured $5 million in seed funding, with the round led by Lightspeed Venture Partners. Kempf is the lead developer behind the ubiquitous open-source software VLC Media Player. The central engineering question is why the architect of a desktop video player is best positioned to build the nervous system for advanced physical AI. Kyber is building an open-source SDK layered squarely on top of the VLC and FFmpeg cores. By leveraging decades of video streaming optimization expertise, Kyber's engineering team has finally achieved an 8 millisecond glass-to-glass latency rate. This rate applies to a dense, synchronized payload, high-definition video and spatial audio, environmental sensor data, and mechanical control inputs. Standard one-way video streaming can buffer data in advance to hide network instability. Remote machine operation requires everything to move bidirectionally in real time, removing that buffer entirely. The core routing SDK remains open source, allowing for wide developer experimentation, while Kyber sells productized, scalable versions directly to enterprise clients. The path to zero-lag robotics relies entirely on optimizing proven media encoding techniques to seamlessly shuttle logic across the global network. To achieve 8 milliseconds, the transport layer must manage highly heterogeneous data streams. Video and audio feeds are bandwidth-intensive chunks of information. Conversely, the telemetry and mechanical control inputs steering the machine are tiny, rapid-fire packets. The network must multiplex these data sizes, weaving them together into a single continuous stream. When multiplexing over standard web protocols, packet queues form. The heavy video data hogs the pipeline, trapping critical steering commands in traffic. If an operator sends a command to turn left, but that packet arrives after the visual frame showing an obstacle, the machine crashes. A synchronized transport layer allows different data types to merge without collision, flowing in parallel without one stream choking the other. The inherent structure of the FFmpeg core was designed to multiplex varied media streams. Kyber has hyper-optimized this stack, modifying the architecture for bidirectional, real-time control rather than passive media playback. By stripping out the cryptographic overhead and handshake protocols required by standard web transit, they clear the pipeline. Reliable teleoperation relies on the flawless, jitter-free synchronization of dissimilar data, as the physics of network transit offer no room for delay. Kyber budgets its data transit using a latency Gantt chart, capped at a hard boundary of 10 milliseconds. The first time allocation goes to the hardware on the machine, the edge capture, where the camera sensor processes the light. Next is the edge encode. This is where the VLC core compresses the raw sensor data, occupying a thin slice of the total time budget. When the data hits the open network, it is governed by physical constraints, the speed of light, and the geographic routing of fiber optic cables. Kyber's SDK manages the fluctuations and packet drops of real-world networks to ensure this transit phase does not blow the timeline. Once the data reaches the operator, time is allocated for the client-side decode, reversing the compression applied back at the edge. Finally, the uncompressed data undergoes the display render, painting the pixels onto the operator's monitor. A standard legacy IT pipeline running through this same process massively overshoots our 10 millisecond threshold. By tuning every step of the encoding and decoding process, Kyber fits the combined pipeline into 8 milliseconds. Sub-10 millisecond teleoperation is achieved through a ruthless elimination of software inefficiencies at every node. The ultimate goal is expanding this model into a network topology capable of managing millions of distributed machines. Managing millions of machines concurrently while maintaining a strict 8 millisecond latency for every connection requires a centralized SDK built for massive concurrency. Kyber is focusing on 3 primary industries where real-time connectivity is mandatory. The first vertical is robotics and humanoids, focusing on zero-lag physical AI operations. A bipedal humanoid generates immense sensor data just to maintain balance. Operating it remotely requires the synchronized multiplexing provided by the Kyber SDK. The second target is drones, powering real-time synchronization for precise remote fleet operations. The third vertical is the remote IT access market, positioning this pipeline as a high-speed alternative to legacy tools. This approach has already secured active deployments across the defense, telecommunications, and AI sectors. To support this rollout, Kyber employs a 25-person engineering team distributed across Paris, San Francisco, and Singapore. The mass deployment of autonomous machines will be determined by the invisible infrastructure layer connecting them to the world.